Welcome back to the Professor's Du Bois channel. This is Professor Victoria and Professor Corey, and we are continuing our buffer series. This is part 4, and today we are going to learn how to make a buffer, and we're going to use the direct addition today, and we're going to have another video that shows you a way to make them with a reaction. So here we go.
Why don't you just briefly describe what direct addition even means?
Yeah, direct addition means that we are going to physically add an amount of our weak acid with an actual amount of our conjugate base. So maybe there'll be volumes and we have to measure out a volume. Maybe there'll be masses and we can use just to measure out the mass of the amount that we need. So we have a specified pH that we want to prepare, and today we need to prepare 1 liter of a buffer with pH 5. Now we haven't talked about how to choose the correct system for a specific pH. So do you want to talk about that?
Yeah, so what you want to do is you want to choose a system that has a pKa as close to the pH, your desired pH, in this case 5, as possible. And, you know, the rule of thumb is that the pKa should be plus or minus 1. So we desire a pH of 5, and looking at these different weak acid conjugate base systems, our best choice is going to be this one with a pKa of 4.19. So that is the closest to 5. So we're going to use the HC2O4 minus weak acid. And you know me, I'm going to write that hydrolysis reaction.
Mm-hmm. So this table was nice. It gave us our weak acid and defined the conjugate base, but you could have just donated the H plus from that and determined that your conjugate base was the C2O4 ion. So here's our hydrolysis reaction, and we need to add the potassium salt of our acid with some amount of our potassium salt of our base, because both of these are ions, and that's okay.
So that's ultimately going to be KHC2O4, and this is something you might be able to find in your stockroom where you won't find a bottle of ions. And so that's going to be our acid salt, and this will be K2C2O4 will be our base salt. We'll need those later.
So we need to figure out ultimately, we need to figure out how many grams of each of these we need, but we are going to first figure out how many moles of each of these we need. So we need the ratio of our moles to acid that we need to be able to create the buffer that will result in a pH of 5. So that's how we're going to start. We're going to use this Henderson-Hasselbalch equation. We know the pH we want. We know the pKa of the system that we chose. And what we're going to solve for is this base over acid. And that's the ratio of our base over our acid.
So the way I'm going to do this mathematically is I'm going to subtract 4.19 from both sides. And then I'm going to take the inverse log, the inverse log, base 10 log. And that's going to leave me with a base over acid value. And the number I got was 6.46. And watch this. This is really important. 6.46 is the same thing as 6.46 over 1. And if I write it like this, that creates a factor. I need 6.46 bases to every 1 acid. And that's going to be really handy because look at this. We want to be 1 molar in our base. So, you know, we can use this factor to figure out what molarity of the acid we need. And I think we're actually going to do that step next, right? Mm-hmm.
So I like to think of this ratio as moles. So we have 6.46 moles of our base to 1 mole of our acid. But our problem here limits us with our weak base. We have to be 1 molar in the weak base. It is just 1 liter. So in this case, you can use moles or you can use liters or molarity because they're the same thing. So we do have 1 mole or 1 molar base, and our ratio is 1 to 6.46. So if we do that division, we end up with, we need 0.155 molar acid. Now, if this was anything other than 1 liter, you'd want to keep this in moles. So you'd have the moles of base that you're limited by, and you'd use that factor. So this is just molarity
in 1 liter.
In 1 liter, so it makes things easy.
So if we have the molar mass of these salts, and we'd have to get these from the periodic table. So all I'm going to do is sum the masses. I've got 4 oxygens, 2 carbons, 1 hydrogen, and 1 potassium. So our acid salt, what's the
molar mass? Is 128.124 grams per mole.
That's the grams in 1 mole. Well, I need 0.155 mole in 1 liter. So I can then multiply 128.124. That's the grams in 1 mole. So my moles cancel, and I'm going to end up with the number of grams I have to put in that liter of my acid salt.
So we end up with 19.86 grams.
Okay, we got an extra digit there because we're at 0.155, but we can round later, I guess. So that's the grams of acid salt. And our base salt
is 1 molar. So we need 1 mole of that, and our grams per mole is 166.21.
So this is base, and that's 166.21 grams in 1 mole of the base. So that cancels. So we're just going to have the 166.21 grams of base salt. And let's clean up those sig figs now. So it looks like we've got 3 sig figs up here in the question, but we see how we got that pKa? The pKa is driven by the Ka with 2 sig figs. Technically, we should be 2 sig figs in this. So this would be 20 grams of the acid salt and 170 to 2 sig figs. But with these are the values that you would get. I think if I was actually making this up, I would go with the 160. I would go a little closer to the 166. But technically, to the correct number of sig figs 2, we would be 20 grams.
Right, and you could look up that Ka to a larger number of significant figures, and that might be a good idea.
That's a good point. So we've got one for you to try, and so again, we're going to prepare 1 liter of a buffer solution. Our desired pH is 7.35, so you're going to have to choose a conjugate acid-base system from this list of 3. And then we're using, this time, the sodium salt. So that's going to be a little bit different as far as molar mass goes. So why don't you pause the video, give this a try, pretty similar to the last one, and then we'll quickly walk through this. Okay, so I'm going to choose this weak acid conjugate base system with a pKa of 7.21. That's close to 7.35. And I do like to write my my acid hydrolysis, and it's not really necessary, but old habits are tough to break. So I'm just going to do this quick. What I really need to find out is that ratio, right? I mean, but this is my...
That's a system.
There's my buffer system. I've got my acid here, and I've got my base. Notice they're ions, so we're going to need to get a salt of these, and they told us to use the sodium salt. And that's a logical choice. The sodium salts are quite soluble. So let's do our, let's use the Hasselbalch equation. We have got a desired pH of 7.35. And that's going to equal the pKa, which is 7.21, plus the log of my base over acid. And this is what I want. I want that base over acid ratio. So the way I'm going to solve for this, I'm going to subtract 7.21 from both sides and then take the inverse log. And I get a ratio, or I get a value of 1.38. This is really important. 1.38 over 1. Same thing. I can put any number over 1. Doesn't change the number. But this really helps me see that I have 1 acid to 1.38 bases.
And I'd like you to use moles here. So even though we are in 1 liter, and we can use molarity, if you get into the habit of saying that this is 1.38 moles of our base to 1 mole of our acid, we can convert whatever is given in the problem. So this is 0.15 molar weak acid. If we had anything other than liters of 1, we could change that into moles, and that would be how we're limiting. So if you just write 1.38 moles of base over 1 mole of acid, and then convert your 0.15 molar to moles, even though it seems silly.
Oh, I see. So you want to go mole per 1 liter times 1 liter.
Yeah, so we're restricted. We have 0.15 moles of our acid. And now we can use our conversion factor that we just solved for using our Henderson-Hasselbalch to get the moles of our base.
Yes. So if we have 0.150 mole acid, I can put that over 1. Now I'm going to use this factor, and I'm going to cancel acid. 1 mole acid, 1.38 mole base. See how the mole acid cancels? I'm left with moles of base. I just have to multiply 0.150 times 0.138, and I get 0.207 mole base. Now it's going to be in 1 liter, so that's also going to be the molarity.
But first we're going to go to grams from moles anyway.
Sure. So we have to get our sodium salt of our acid and figure out how many grams to get 0.150 moles of that acid. So the sodium salt of the acid, I go back up here to my acid. This is H2PO4 minus. That's going to be NaH2PO4. So that's sodium salt, acid. And the molar mass of that?
So we're going to have
Is that
0.150 moles times 119.975 grams in 1 mole.
And that's just the molar mass from the periodic table.
And that gives us 18.0 grams of our acid salt.
Okay.
Sodium dihydrogen phosphate.
Now the base here is going to be Na2HPO4.
And remember, we needed 0.207 moles of that.
That's what we solved for up here.
So how many grams of that sodium salt? We're going to use the molar mass of 141.958 grams in 1 mole from the periodic table. 2 sodiums, 1 hydrogen, 1 phosphorus, 4 oxygens. And we get 29.4 grams of that sodium hydrogen phosphate salt. Now we know by direct addition we can add those two together in this case 1 liter, and we will have our buffer of, what was it, 7 something.
Looks like we're going to have a buffer at 7.35.
All right.
That's fantastic.
There we go.
There's a little sneak preview into the next video.
Little sneak. Yeah, we're going to do another one. We've got a couple more videos in this series for our buffer calculations, and hopefully you will join us for that. Like, subscribe, and hit that notification bell. Have a great day. Bye-bye.